Hello everyone, this is week 9 for Applied Statistical Analysis. Today we're going to be talking about relationships, not the kind that the marriage and family therapists want to talk about, but relationships nonetheless. The way we're going to look at relationships is through correlation and regression. So we'll talk about both of those, just an intro to regression today, but we'll get into correlation. This is all discussed in chapter 13 of the book. I think it's not discussed nearly as much. So we're going to spend a couple weeks on this material, even though it's only one chapter in the book. So far in this class, we focused on comparing means. So we kept asking a similar question: is one group different than the others? We use z-test, t-test, and ANOVA. And we compare the means and use the variability within the groups to decide if the difference is significant. So that's what we've done. Everything so far is just, are these groups different? What we're introducing now is we're going to be able to ask the question, is there a relationship between two variables? So we're going to use correlation and regression for this. And ultimately what we're trying to do is we're looking at how much the variables move together. So in this example right here, this little graph, if you go up in this variable, what happens to the other one usually? Well, it tends to go up. So this would be a positive relationship. As this one goes up, this one also tends to go up. That's what that line is telling us. So we're going to be looking at that in detail today. So when you hear the word correlation, it's used a lot in regular terms around the world. In stats, it's talking about a whole class of methods that generally you're using with observational data. It has similar assumptions to a t-test, and it's also a measure of effect size. So it'll tell us the direction and the strength of a relationship between two variables. What's cool is that it's very related and actually based on z-scores. So everything we learned about z-scores, that's still going to be relevant here. Just to remind you, z-score is a univariate statistic. It's only used in one variable. We've done this, it basically centers the variable and puts it into standard units. Correlation is essentially the z-score between two variables. So the term we often use for it is R. And so the Pearson's R is one of the most common forms of correlation. It's just the sum of the z-scores after you've times them together, divided by n minus 1. We're going to get into the logic of this pretty soon, but just so you're aware, the z-score, this one right here, that's a z-score of your x variable, and this one's a z-score of the y variable. We'll talk about why this works in a little bit, but this equation actually is everything that it takes to understand the correlation between two variables. When it comes to actually running correlation, you need two or more continuous variables. Here's an example. var1 is continuous, var2 is continuous. Another thing about correlation is it's not necessarily directional. We're not saying one causes the other, we're just saying they move together, they go together. And last thing that we absolutely need is that the relationship needs to be linear, or at least roughly linear, or in other words, ordinal. So if one goes up, the other one goes up, or one goes up, the other one goes down. If it curves a lot, then the correlation is not going to be able to help you. And we'll do some of those examples in class. Probably not shocking, the hypothesis testing with correlation is going to use the exact same 6-step approach. First is the assumptions. We still want our data to be independent. So individuals are independent of each other. So one person's scores on their variables do not affect someone else's. We want interval ratio variables for the appropriate measurement. Technically, correlation wants multivariate normality. In other words, the two variables are jointly normal. This is hard to envision, but basically if both are normal, then usually you will have something like multivariate normality. Again, just like all the normality assumptions, when our sample's really big, these become far less important. Lastly, is it's homoscedastic. So its variance around the line should be roughly equal across the whole line. I'll show some examples, but basically it just means the variance, no matter where you're at along any of the variables, the variance is roughly the same. The way we're going to check this, basically everything is the same up to this point. Where for homoscedastic, we're going to do scatter plots. Step 2 is stating the null and research hypotheses. So symbolically, it's going to be rho. I know that looks like a cursive P, but it's called rho. So the research hypothesis is that rho is not equal to 0. That says the correlation is not 0. The null hypothesis is that the correlation is 0. If the null hypothesis is true, that means any differences we're seeing, so if our rho or our R value, our correlation is not exactly equal to 0, it's just due to random chance or sampling error. It's not real. If the research hypothesis is right, then it means there's a relationship between the variables. We always need to define critical regions. For this class, we're just going to rely on the classic alpha equals 0.05. Step 4, I'm going to walk through a few things on how to do this in Jamovi, just right here, just so you can see it. First thing, we go to regression and click on correlation. It may look slightly different in the updated Jamovi, but it'll look very similar to this. From there, we bring all the variables we want to correlate, and they go here in this box. We select a number of things. If your variables are continuous, we'll often do Pearson. We also want to report significance. Generally, the hypothesis is going to be correlated, and then we can get plots to take a look at what the data look like. When we do all this, this is what we get. We get a correlation matrix, which looks just like this. We're going to talk about this a lot more in class, but so you can start to see what different pieces mean. The pretest, so this is pretest and pretest. So when pretest is correlated with pretest, it doesn't give us a value because it's not very informative. When you have one variable correlating with the exact same variable, you always get a correlation of 1. It's just how it works. So it doesn't even report it. So pretest with pretest, nothing. Pretest with post-test, now we're getting some information. So the Pearson's R is right here. It's 0.086, and our p-value is 0.718. So here, this is not significant. The p-value is way above our 0.05 cutoff, and so we would fail to reject the null. Even though this is not exactly 0, we would expect that it's likely due to just sampling error. What's nice is the plots also give you some information. So this plot right here shows you the distribution of the variable. Does it look roughly normal? And here, maybe it's a little bit skewed to the right or skewed to the left. The hump is more towards the top. You kind of have this, ceiling effect maybe. Post-test looks a lot more normal. And this one tells us the correlation. We already have that up here. And then here it shows a scatter plot, which tells us a lot of information about how the dots are scattered around the line. Here, we don't have a very big sample, but this is looking decent. We'll talk about this more in class. So the reason why that calculation that I showed earlier, the The reason why it works is because of how z-scores work. Let's take a look at this graph and talk about what the z-score would be. We have x down here. Let's say this is the mean of x. All the x values on this side would be positive values. All the ones on this side would be negative. And any points right at the mean would be 0. Same goes for y. Anything above here would be positive. Anything below here is negative. In this situation, we have a positive relationship between x and y. If you drew the best fitting line between all these points, it would look something like this. The reason why is you have more points in this quadrant, here and here, which is, in both cases, this score is a positive z-score for x and a positive z-score for y. So when we times both positives together, we get a positive. So this one right here is a positive value that gets fed into the correlation. This one, also positive. It's on this side of the x mean, and it's on this side of the y mean, so this one's positive. Positive times a positive, if we go back to the equation. So if this is positive and this is positive, a positive times a positive is a positive. So we go back. And so you can see the pattern. All of the ones in this quadrant over here are going to be positive times a positive. So all of these contribute positive values. Over here, this one, this is below the mean, so it's a negative x, and it's a negative y. So this one's a negative times a negative, which is also a positive value. So all the values over here are also positive values for the correlation. Here and here are going to be positive. Positive times a positive is a positive. Negative times a negative is a positive. Over here you have a positive x, but a negative y. That means these 2 points are going to be negative values for the correlation. Positive times a negative is a negative. Positive times a negative is a negative. You have the same thing happening here. And roughly, what you can look at is where are most of the points? Are most of them in the positive areas or in the negative areas? If more points are in the green, the positive areas, then the correlation is going to be positive. And conversely, if more points are in these red places, the negatives, then the correlation is going to be negative. I'm hoping you can kind of see how the z-scores matter here, because it's all about z-scores. Is it a positive z-score or a negative z-score? When you times those together, that helps you understand what direction that point is helping the correlation to go to. Another thing to note is the points that are further away from the means are going to have a bigger influence. So this point and this point are going to have a bigger value than this point and this point. So if you have more points out here especially, that's going to be more influential. One of the main effect sizes for correlation besides correlation itself is actually R squared. You just square the correlation and that gives you an effect size. It's going to be closely tied to what we did with eta squared. They're similar in a lot of ways. The R squared is interpreted as the amount of variance in one of the variables that the other variable explains, or in other words, how much variance do they have overlapping with each other? In other words, how much do they overlap their information? And then lastly, we interpret the results. So we would state what the correlation is, what it means, what direction it is, all that stuff. There is an example on page 529 if you want to take a look at that. And now we'll move on to regression. Correlation and regression are intimately tied. They're in a lot of ways the same thing. Regression just lets you do a little bit more. That means here I'm just going to give you an intro, just give you a rundown of what is happening in regression, why we use it. And then next week we'll get into it a lot more heavily. You can think of regression as the foundation of almost everything we do in statistics. It can compare group means, so it can do what ANOVA and t-tests do. It assesses relationships, so it can do what correlation does. And it can do both at the same time. In other words, it's like taking the best of t-tests, ANOVAs, and correlation and gluing them all together. It's all regression. What's great is it can handle many types of outcome and predictor data types. So you're not stuck with just a specific subset of things that you can do. You can use regression in tons of situations. So there's two main types of regression. First one is simple. What tells you that it's simple is you only have one predictor in the model. You have an outcome and a predictor, just one predictor. When variables are standardized, the simple regression gives you the same results as correlation. They're identical. When using a grouping variable, it's the same results as a t-test or ANOVA. That means you can think of t-tests, ANOVAs, and correlation as just special forms of simple regression. There's also multiple regression. You know that it's multiple regression because you have more than one variable in the model or more than one predictor. You have one outcome and then you might have two predictors predicting that outcome. That would be a multiple regression. We'll get into multiple regression a lot more next week. But when variables are standardized, it gives you a rough estimate of the partial correlation. Not exact, but very similar. The predictors can be any combination of categorical and continuous, which is great. You can have groups and continuous variables in the same regression analysis. Regression, what it's trying to do when you have continuous variables, it's just trying to find the best fitting line. The way we define this is by minimizing the difference between the points and the line, which are called residuals. So all we're trying to do is make this distance between the point and the line as small as possible. If this is the best fitting line according to that definition, then any other line that you could possibly draw through these points would have bigger residuals than that line. If you get really nerdy, it's actually really cool. There's a ton of cool stuff that you can just use using the best fitting line. We're going to talk about that a lot more next week. But the idea is always going to be the same. Regression is trying to find this best fitting line, the line that represents those points the best. Another thing to know is the line always goes through the averages of x and y at the same time. So if this is the best fitting line, it will go through that point where the average of x and the average of y intersect. Keep all this in the back of your mind. Remember that regression is this really flexible tool. We'll get into a lot more depth next week. I just wanted to help you see what was coming, be able to be thinking about it in the meantime. And if you have questions, as always, post them to the discussion board before class starts, and we'll try to get to them during the class. We'll go over Jamovi in more detail of how to do this and provide some examples.